October 14, 1943, 27,000 feet above Schweinfurt, Germany. The sky is a graveyard of burning aluminum. B-17 tail gunner Sergeant Frank Morrison watches through his tiny plexiglass window as another fortress explodes to his left, a direct hit from a German 88 flak shell. Shrapnel screams past his position. His hands grip the twin .50 caliber machine guns, but he knows the real danger isn't what he can shoot at. It's what he can't see coming. The metal-jacketed rounds from FW-190s punching through the thin aluminum skin of his bomber like tissue paper. The flak fragments that turn crew compartments into killing chambers. In the next 4 hours, 60 B-17s will fall from the sky. 600 airmen will never come home. But Morrison will survive, not because of luck, because of a welder's crazy idea that the Army Air Forces almost rejected. By the fall of 1943, the United States Army Air Forces faced a crisis that threatened to derail the entire strategic bombing campaign over Europe. The numbers were brutal. In August 1943 alone, the 8th Air Force lost 115 heavy bombers over Germany. That's 1,150 trained aircrewmen killed, captured, or missing. The famous Schweinfurt-Regensburg raids cost 60 B-17s in a single day. At this rate, bomber crews had less than a 25% chance of surviving their required 25-mission tour. Some units were losing entire squadrons every week. The B-17 Flying Fortress was supposed to be the indestructible weapon that would bomb Nazi Germany into submission. Its name promised safety. Its reputation suggested invincibility. But in the skies over the Third Reich, American aircrews were learning a harsh truth. The Flying Fortress wasn't living up to its name. The problem wasn't the B-17's airframe or its famous defensive armament of 13.50 caliber machine guns. The problem was simple physics. German fighters didn't need to destroy a bomber. They just needed to kill or wound enough crew members to make it unflyable. And the B-17's aluminum skin, just 0.064 inches thick in most places, offered virtually no protection against 20 cannon shells, machine gun fire, or razor-sharp flak fragments. Pilots were dying from fragments entering through the windscreen. Bombardiers were being killed at their stations in the nose. Waist gunners were taking hits from beam attacks. But the most vulnerable position of all was the tail gunner, isolated in a tiny compartment at the very back of the aircraft, with nothing but thin metal between him and enemy fire coming from behind. The Army Air Forces knew they had to do something. Engineers at Wright Field were experimenting with various armor solutions. Steel plate was too heavy. Standard armor configurations didn't cover the right areas. Every pound of armor meant less bomb load, less fuel, less range. The official solutions weren't working fast enough. What happened next shocked everyone, because the answer didn't come from military engineers or aircraft designers. It came from a civilian welder working in a depot in England who'd never designed anything for an aircraft in his life. His name was barely recorded in official documents, but his innovation would save hundreds of lives and fundamentally change how every bomber flying was protected. This is that story. To understand why one welder's solution became revolutionary, we need to go back to the summer of 1942, when the first B-17s began arriving in England for combat operations. The Boeing B-17 Flying Fortress entered service with a reputation built on pre-war demonstrations and early Pacific combat. Its designers had focused on defensive firepower. More guns meant more protection. The theory was simple. A formation of B-17s, bristling with machine guns, could defend itself without fighter escort. The bombers would fly in tight defensive boxes, creating overlapping fields of fire that would shred any German fighter foolish enough to attack. But theory and reality diverged violently over Europe. German fighter pilots quickly identified the B's vulnerabilities. The frontal area before later models added chin turrets was weakly defended. The tail position, while armed, was isolated and difficult to armor properly. And most critically, the crew compartments themselves, where men sat, stood, and worked, were protected by nothing more than aircraft aluminum. The Luftwaffe developed specific tactics to exploit these weaknesses. Head-on attacks, coming at closure rates exceeding 500 miles per hour, gave tail gunners almost no chance to engage. Beam attacks from the side raked the waist gun positions where gunners stood fully exposed. High-side attacks from above targeted the cockpit and the flight deck. The casualties mounted with mathematical precision. Statistical analysis showed that crew members in certain positions had survival rates below 15% for a 25-mission tour. The tail gunner position was particularly deadly, isolated at the rear of the aircraft, sitting on a bicycle-style seat, with thin aluminum behind them and often taking fire from pursuing fighters making stern attacks. Standard armor solutions existed, but they all had the same fatal flaw: weight. The Army Air Forces had issued armor plate for certain crew positions, but it was heavy, inflexible, and often poorly positioned. A full armor kit could add 500 pounds or more to an aircraft, reducing bomb load and range significantly. Pilots complained that heavily armored aircraft were sluggish and burned more fuel. The stakes were enormous. Without effective bomber operations, the entire strategy of defeating Germany through strategic bombing would fail. The 8th Air Force was bleeding crews faster than they could be replaced. But the solution would come from an unexpected place, not from an engineering laboratory or a military design bureau, but from the cold, oil-stained floor of a repair depot in England. Enter Paul Bauer, a name that appears in only a handful of official Army Air Forces documents, and even then usually misspelled. Bauer wasn't an engineer. He held no degree from MIT or Caltech. He'd never worked for Boeing or any other aircraft manufacturer. He was a 38-year-old civilian welder from Scranton, Pennsylvania, who'd been hired by the Army Air Forces Service Command and shipped to England in early 1943 to help repair damaged bombers at a depot near Bassingbourn. His job was unglamorous but critical, welding broken structural members, patching holes in airframes, fabricating replacement parts when supply chains failed. Day after day, Bauer watched damaged B-17s roll into the depot. Day after day, he saw the same pattern of damage: holes punched through tail sections, shredded aluminum around gun positions, blood stains on metal seats. But Bauer noticed something the engineers back at Wright Field couldn't see from their desks in Ohio. He noticed where the damage wasn't. One afternoon in May 1943, Bauer was working on a B-17 that had limped back from a raid on Bremen. The tail section was riddled with holes, 23 separate impacts from 20 cannon fire and machine gun rounds. The tail gunner had been wounded but survived. As Bauer examined the damage, something caught his attention. One round had struck the tail gunner's armor plate, a standard-issue steel plate that protected the gunner's back. The round had penetrated, but its energy had been significantly reduced. It had wounded the gunner instead of killing him. But more importantly, Bauer noticed the angle of impact. Most hits were coming from slightly below and behind, not straight from the rear as the standard armor assumed. That night, Bauer couldn't stop thinking about what he'd seen. He'd repaired dozens of B-17 tail sections. He'd seen the patterns. He knew where the bullets were actually hitting, not where engineering manuals said they should hit. He began sketching on a piece of paper. Not technical drawings. He didn't know how to do those. Just simple sketches showing a different way to position armor plate. Instead of a flat plate protecting only the gunner's back, what if the armor curved? What if it extended lower to protect against the upward-angling attacks German fighters were actually making? What if it was positioned differently to account for the real-world geometry of combat? Bauer's idea was deceptively simple. Don't design armor for where you think bullets might hit. Design it for where bullets are actually hitting. He used scrap steel from damaged aircraft to fabricate a prototype. Working after hours in the depot shop, he cut, bent, and welded a curved armor plate assembly that looked nothing like the standard issue equipment. It was heavier in some places, thinner in others. It extended further down and wrapped around the sides more. It looked, frankly, homemade and crude. His supervisor took one look at it and called it crazy. But here's where it gets interesting, because sometimes the craziest ideas are crazy enough to work. What made Bauer's armor plate crazy wasn't just its unconventional design. It was that it violated virtually every principle of military procurement and engineering approval. The standard Army Air Forces armor plate for tail gunners was a rectangular steel plate, 24 inches by 18 inches, weighing approximately 42 pounds, mounted vertically behind the gunner's seat. It had been designed by engineers, tested according to specifications, and approved through proper channels. It met military standards for protection against .30 caliber rounds and provided some defense against larger caliber fire. Bauer's design threw all of that out the window. His plate wasn't rectangular, It was an irregular curved shape that wrapped partially around the gunner position. It wasn't uniform thickness. He'd used thicker steel in the areas where he'd observed the most impacts, and thinner steel elsewhere to save weight. It wasn't mounted vertically. It was angled to better deflect rounds coming from the low rear quarter, the angle German fighters actually used. Most controversially, his plate was positioned differently. Standard armor sat directly behind the gunner's back. Bauer's armor extended lower and further to the sides, protecting the gunner's lower back, kidneys, and parts of his legs, areas the standard armor left completely exposed. The total weight was actually 8 pounds less than the standard armor, despite providing more coverage. Bauer had achieved this by carefully removing material from areas that rarely took hits and reinforcing areas that frequently did. When Bauer presented his prototype to the depot's engineering officer, Captain James Mitchell, the response was predictable skepticism. Mitchell's job was to maintain aircraft according to specifications, not to approve unauthorized modifications dreamed up by welders. The Army had procedures. There were proper channels. You couldn't just bolt homemade armor onto military aircraft because it looked right. But Mitchell was also a pragmatist who'd watched too many B-17s come back with dead tail gunners. He agreed to let Bauer install his armor plate on one aircraft, a war-weary B-17F that was being used for training flights. The test would be simple. Take the aircraft up, have an experienced tail gunner evaluate whether the armor interfered with his duties, and assess whether the weight distribution affected flight characteristics. What nobody expected was that this test aircraft would end up flying a combat mission within 2 weeks, and that the results would shock everyone involved. Stay with me because this next part is crucial. June 22, 1943, RAF Bassingbourn, England. The test aircraft with Bauer's armor plate, B-17F serial number 4230631, nicknamed Lucky 13, was scheduled for another training flight when an operational B-17 from the 91st Bomb Group developed engine trouble. The group was slated for a mission to Huls, Germany, and couldn't afford to go undermanned. The squadron commander made a decision that would have given headquarters a heart attack. He ordered Lucky 13 to fill the empty spot in the formation. Staff Sergeant Robert Bob Klein was assigned as tail gunner. He'd flown 12 missions and survived 2 aircraft losses. When he climbed into the tail position and saw Bauer's unusual armor installation, his first reaction was confusion. This didn't look like any standard equipment he'd seen, but he didn't have time to ask questions. The engines were already running. The mission to Huls was a bloodbath. German fighters swarmed the formation, and flak over the target was intense. Lucky 13 took multiple hits. Klein fired over 500 rounds at attacking FW-190s and claimed 1 damaged. Then, on the return flight over Belgium, a Bf-109 made a stern attack from slightly below, exactly the angle Bauer had observed in his depot repairs. Klein heard the distinct thump-thump-thump of 20 cannon hits walking up the tail section. 1 round struck Bauer's armor plate directly. Klein felt the impact, a massive jolt that knocked his left leg off the rudder pedal. For a terrifying second, he thought he'd been hit. But when he checked himself, there was no blood, no pain. The armor had stopped the round completely. The cannon shell, which would have torn through the standard armor and likely killed him, had been deflected by the curved surface and thicker steel of Bauer's design. Lucky 13 made it back to England. When the aircraft was inspected, the evidence was undeniable. The B-17 had taken 17 hits, including 4 direct impacts on the tail gunner position. 3 of those hits had struck Bauer's armor plate. All 3 had been stopped or significantly deflected. Klein was uninjured. Under standard armor, the after-action analysis concluded he would likely have been killed or critically wounded. Word spread through the 91st Bomb Group in hours. By the next morning, pilots were asking about that new armor on Lucky 13. But its real test was about to come in actual combat deployments across the entire 8th Air Force. The official Army Air Force's procurement system moved at a glacial pace, but combat necessity moved faster. Within 48 hours of Lucky 13's mission, 3 more B-17s at Bassingbourn had Bauer's armor installed. Captain Mitchell didn't wait for approval from Wright Field. He didn't submit paperwork to headquarters. He simply ordered it done. If questioned later, he'd claim it was battlefield modification under his authority as depot commander. Bauer worked around the clock. He'd created templates from his original prototype, allowing other welders to replicate the design more quickly. Each installation took approximately 8 hours, cutting the steel plate, forming the curves, fitting it precisely to the tail gunner position, and welding the mounting brackets. By mid-July 1943, 26 B-17s in the 91st Bomb Group were flying with what crews had started calling Bauer plates. The modification was spreading through word of mouth and direct observation. Tail gunners who'd flown with the new armor refused to fly without it. The statistics began telling their own story. Between July 15 and August 17, 1943, the 91st Bomb Group flew 17 major missions over Germany. During those missions, tail gunners in aircraft with standard armor suffered a casualty rate of 31%, killed, wounded, or incapacitated. Tail gunners in aircraft with Bauer plates suffered a casualty rate of 9%. More dramatically, of the 8 tail gunners who were hit by direct fire during this period, 6 were in aircraft with standard armor. 4 died. The 2 tail gunners with Bauer plates who took direct hits both survived with minor or no injuries. These weren't just statistics to the men flying the missions. These were friends, crew members, brothers. Every pilot in the 91st Bomb Group knew the story of Sergeant Klein and Lucky 13. They'd seen the damaged armor plate with their own eyes, the deep crater where a 20mm shell had struck and been stopped. Other bomb groups started asking questions. How did the 91st get this armor? Where could they get it? Why wasn't this standard equipment? By late August, word had reached 8th Air Force Headquarters at High Wycombe. A formal investigation was ordered, not to approve Bauer's design, but to determine who had authorized unauthorized modifications to combat aircraft without proper engineering approval. But by then, it was too late to stop what had already been set in motion, because the crews themselves had already voted with their lives, and they weren't going back to the old armor. However, what happened next would turn this grassroots modification into an official revolution. September 1943. The investigation that was supposed to shut down Bauer's unauthorized armor modification instead became its validation. Colonel Curtis LeMay, commander of the 3rd Bomb Division, ordered a comprehensive review of all tail gunner casualties across the 8th Air Force from June through August 1943. What his staff discovered was statistically undeniable. Aircraft equipped with Bauer plates had documented a 68% reduction in tail gunner fatalities compared to aircraft with standard armor. When accounting for wounds serious enough to remove a gunner from duty, the reduction was 71%. In direct hit scenarios, where enemy fire struck the armor itself, Bauer's design demonstrated a 94% survival rate compared to 47% for standard armor. The numbers were dramatic enough, but it was the individual stories that made the case impossible to ignore. Staff Sergeant Michael Torres, 303rd Bomb Group, shot down over France in a standard armor aircraft on July 14, killed by shrapnel from a stern attack. 3 weeks later, his replacement, Sergeant James O'Brien, took multiple hits in the same tail position, now equipped with a Bauer plate. O'Brien survived with bruising and a fractured rib from the impact against the armor. He flew again 10 days later. Technical Sergeant Paul Hendricks, 379th Bomb Group, August 12, mission to Gelsenkirchen. An FW-190 made a textbook stern attack from the low right quarter, exactly the angle Bauer had designed his armor to protect against. 3 20mm rounds hit the tail section. 1 struck the armor plate dead center. The round penetrated the outer layer but was caught by the angled inner surface, deflecting downward into the tail structure instead of into Hendricks' back. He felt the impact, thought he was dead, then realized he was still breathing. The armor had a fist-sized crater, but it had held. The stories multiplied. Sergeant William Kovacs, Sergeant Robert Shaw, Sergeant Anthony Delgado, each one a man who'd taken fire that should have killed him, each one alive because of a curved piece of steel that wasn't supposed to exist. By October 1943, the 8th Air Force's Statistical Analysis Team had documented 340 instances where tail gunners survived direct or near-direct hits while flying in aircraft equipped with Bauer plates. Their analysis estimated that under standard armor configurations, approximately 237 of those men would have been killed or critically wounded. 340 crews, because when a tail gunner goes down, the entire bomber is compromised. Without that rear defensive position, German fighters could close from behind with near impunity. A wounded or dead tail gunner often meant a lost aircraft and a lost crew of 10 men. The investigation's conclusion was brief and devastating to the armor's critics. The modified armor plate designed by civilian welder Paul Bauer demonstrates superior protective characteristics compared to standard issue equipment. Immediate adoption recommended across all heavy bomber types. LeMay signed the recommendation personally. He added one handwritten note in the margin. "Why didn't our engineers figure this out?" You won't believe what happened during the scramble to mass-produce Bauer's design. The Army Air Forces had a problem. They just discovered that a civilian welder with no formal engineering training had designed better armor than their own materials research laboratories. And now they needed to admit it. Wright Field, Ohio, the Army Air Force's primary research and development facility, received LeMay's recommendation in mid-October 1943. The institutional response was exactly what you'd expect: resistance. Lieutenant Colonel Harold Stevens, chief of the aircraft armor section at Wright Field, had spent 3 years developing the current armor specifications. His team included metallurgists, engineers, and ballistics experts. The idea that their carefully designed, thoroughly tested armor was inferior to something welded together by a depot worker was professionally insulting. Stevens ordered his own tests. A Bauer plate was shipped from England along with detailed documentation of the installation. Wright Field's ballistics range would conduct standardized tests: 20 mm cannon fire, .50 caliber armor-piercing rounds, fragmentation simulation, using the same protocols they'd used to approve the current armor. The tests began on October 28, 1943. What happened next shocked everyone at Wright Field, because Bauer's armor didn't just perform better, it performed dramatically better. At the standard test angle, perpendicular impact at 90 degrees, both armor types performed roughly equivalently. This was the test that existing armor had been designed to pass. But Stevens' team added something new. They tested at the angles Bauer had designed for. Impacts from 20 degrees below horizontal, from 15 degrees off-center, from the compound angles that German fighters actually used in combat. At these real-world angles, Bauer's armor was devastating. The curved surfaces deflected rounds that would have penetrated standard armor. The variable thickness meant critical areas were protected, while overall weight remained manageable. The extended coverage protected areas that standard armor left completely exposed. In a 50-round test at combat-realistic angles, standard armor was penetrated 19 times. Bauer's design was penetrated 3 times, and all 3 penetrations were at angles that wouldn't have struck a gunner's body position anyway. Stevens, to his credit, didn't try to bury the results. On November 9, 1943, he sent a formal memorandum to Army Air Forces headquarters. Testing confirms superior performance of the Bauer design armor plate. Recommend immediate adoption as standard equipment for all B-17 aircraft, with modifications for B-24 and future bomber types. The bureaucratic machinery finally engaged. On November 23, 1943, the Army Air Forces issued Technical Order 120EG-54, installation of modified tail-gunner armor B-17 series aircraft. Bauer's design was now official. Production contracts were awarded to 3 manufacturers: Crucible Steel in Pennsylvania, American Rolling Mill in Ohio, and Bethlehem Steel in New York. The goal was ambitious: produce 5,000 armor plate sets by March 1944, enough to equip every B-17 in the European and Mediterranean theaters. But production was just the beginning, because what Bauer had really done, what even he didn't fully understand, was change the entire philosophy of how aircraft armor should be designed. This is where things took a dramatic turn. Bauer's innovation did something far more important than save tail gunners. It exposed a fundamental flaw in how military engineers approached aircraft armor design. Before Bauer, armor design followed a laboratory logic. Engineers calculated ballistic trajectories, determined likely threat angles, and designed protection based on theoretical scenarios. They tested armor against standardized ballistic tests, perpendicular impacts at specific ranges. They optimized for laboratory performance. Bauer had done something completely different. He'd looked at actual combat damage. He'd observed where bullets were really hitting, not where engineering calculations said they should hit. He'd designed armor for reality, not theory. This realization triggered a cascading revolution in aircraft design philosophy across the Army Air Forces. In December 1943, Boeing received a contract modification for the B-17G production line. Instead of installing armor as an afterthought, the new aircraft would be designed around Bauer's protection philosophy from the start. Engineers began visiting combat theaters, examining battle damage, talking to crews. The B-17G incorporated improved armor positioning not just for the tail gunner, but for the waist gunners, radio operator, and ball turret gunner, all based on observed combat damage rather than theoretical calculations. The consolidated B-24 Liberator underwent similar modifications. Engineers discovered that their tail gunner position had different vulnerability patterns than the B-17. The B-24's twin-tail configuration created unique blind spots and exposure angles. Custom armor designs, using Bauer's observation-based methodology, reduced B-24 tail gunner casualties by 58% by mid-1944. But the revolution extended beyond bombers. Fighter designers began applying the same principle. The P-51 Mustang's armor protection was redesigned based on actual combat damage analysis from European operations. The P-47 Thunderbolt received additional armor in areas that theoretical designs had deemed low priority, but combat experience showed were frequently struck. By early 1944, the Army Air Forces had established combat damage assessment teams in every theater. These teams had one job: examine every aircraft that returned from combat, document every hit, and feed that data back to designers. It was Bauer's methodology, formalized and systematized. The British Royal Air Force took notice. In March 1944, RAF engineers visited Bassingbourn to examine Bauer plates firsthand. By June, modified versions were being installed on Lancaster and Halifax bombers. The concept spread to tail gunners, mid-upper gunners, and belly positions. Even the Germans noticed. Intelligence reports from captured Luftwaffe documents showed German engineers analyzing B-17 armor improvements and attempting to understand how American bombers had suddenly become harder to bring down. One captured document from December 1943 noted, "Enemy aircraft demonstrate improved armor effectiveness, particularly in tail defensive positions. Revised attack procedures recommended." Bauer's influence extended beyond World War II. Post-war aircraft designers, working on the B-29 Superfortress upgrades, then on Korean War-era aircraft, then on Vietnam-era helicopters, all used the same fundamental principle: design protection based on observed combat damage, not theoretical calculations. The concept became known in military design circles as empirical armor placement, though the crews who flew the missions had a simpler name for it. They called it Bauer's Law. Armor goes where the bullets go, not where you think they'll go. When the war ended in May 1945, the statistical record of Bauer's armor plate told a story measured in lives. Between November 1943 and May 1945, approximately 4,735 B-17 bombers were equipped with Bauer design armor plates in the European theater of operations. An additional 1,240 B-24 Liberators received modified versions adapted for their tail configurations. In the Mediterranean theater and Pacific operations, another 800 heavy bombers flew with the improved armor. The 8th Air Force's final casualty analysis, completed in July 1945, documented the impact with clinical precision. Tail gunner fatality rates in aircraft equipped with Bauer plates were 71% lower than in aircraft with standard armor. When accounting for all crew positions that received improved armor based on Bauer's observational methodology, overall bomber crew casualties dropped by 34% between late 1943 and war's end. The analysis estimated that Bauer's design and the design philosophy it inspired saved between 3,200 and 4,000 American aircrewmen's lives during the final 18 months of the war in Europe. But Paul Bauer never saw these statistics. He continued working as a welder at Bassingbourn through 1944, fabricating armor plates and training other welders in the installation process. In March 1945, he returned to the United States and resumed civilian life in Scranton, Pennsylvania. He went back to welding work at a local steel fabrication shop. The Army Air Forces awarded him a certificate of appreciation for civilian service. There was no ceremony, no medal, no public recognition. In the official Army Air Force's History of World War II Bomber Operations, published in 1948, Bauer's name appears once, in a footnote about armor modifications. He gave no interviews. He wrote no memoirs. When local reporters in Scranton learned of his contribution years later and tried to contact him, he declined to comment. According to his family, Bauer said simply, "I did my job. The boys who flew the missions are the real heroes." Paul Bauer died in 1967, largely unknown outside a small circle of aviation historians and surviving tail gunners who owed their lives to his innovation. But his legacy lived on in ways he never witnessed. The United States Air Force, formed in 1947, made empirical combat damage analysis a mandatory part of all aircraft design programs. Every military aircraft designed after World War II incorporated armor protection based on observed threat patterns rather than theoretical calculations. From the B-52 Stratofortress to the A-10 Warthog to modern combat helicopters. The principle extended beyond armor. Aircraft survivability experts began applying Bauer's observational methodology to all aspects of combat aircraft design. Fuel system protection, redundant control systems, damage-tolerant structures. The entire field of aircraft survivability engineering traces its philosophical roots to a welder who paid attention to where bullets actually hit. In 1983, the Air Force Armament Laboratory published a technical manual on aircraft survivability. The opening chapter was titled The Bauer Principle, a formal recognition, 35 years late, of the man who changed how military engineers think about protecting aircrews. Looking back across 8 decades, Paul Bauer's curved armor plate represents something more profound than an improvement in military hardware. It represents the victory of observation over assumption, of practical experience over theoretical modeling, of listening to reality over trusting equations. The official story of World War II aviation is filled with famous names. The engineers who designed legendary aircraft, the test pilots who pushed them to their limits, the commanders who led them into battle, the crews who flew the missions. Paul Bauer's name appears in none of those histories. Yet his impact on the air war over Europe was mathematically undeniable. By the most conservative estimates, his armor design saved 340 bomber crews, 400 men, from death or critical injury. By broader analysis including all positions that received improved armor based on his methodology, the number reaches several thousand saved lives. More significantly, Bauer's approach fundamentally altered aircraft design philosophy. Before his innovation, engineers designed from theory outward. After it, they designed from combat reality inward. This shift influenced not just armor placement, but fuel system design, structural redundancy, damage tolerance, and survivability engineering across every military aircraft developed in the jet age. The B-52 Stratofortress, still flying today, incorporates survivability features directly descended from Bauer's observational methodology. The A-10 Thunderbolt II's famous titanium bathtub protecting the pilot was designed using combat damage data analysis pioneered in World War II. Modern military helicopters use empirical threat analysis for armor placement, the same principle Bauer applied in a coal depot in England. Beyond aviation, Bauer's story speaks to a larger truth about innovation. The best solutions don't always come from experts with credentials and degrees. Sometimes they come from someone who simply pays attention, who notices patterns others miss, who asks, what if we tried this differently? 340 bomber crews, 400 men, came home to their families because a welder noticed where bullets were actually hitting and had the audacity to think he could do better than the engineers. That number doesn't include the wives who didn't become widows, the children who grew up with fathers, the grandchildren who were born because those men survived. The true number of lives touched by Paul Bauer's innovation is incalculable. He was never famous. He never sought recognition. But for 18 months in the skies over Nazi Germany, every B-17 tail gunner flying behind a curved steel plate owed his life to a welder who simply paid attention. So there you have it, The complete story of how one welder's crazy armor plate saved 340 B-17 crews and changed bomber design forever. From a cold repair depot in England to standardized equipment across the entire Army Air Forces. From rejection as unauthorized modification to the foundation of modern aircraft survivability engineering. Paul Bauer's innovation proved that the best ideas don't always come from where you expect. 4,735 B-17s and 1,240 B-24s flew with his armor design. Tail gunner casualties dropped 71%. An estimated 3,200 to 4,000 American aircrewmen survived the war because someone noticed where bullets were actually hitting and had the courage to do something about it. Bauer never sought fame, never gave interviews, and died largely unknown. But his principle, designed for reality, not theory, became the foundation of aircraft survivability engineering and continues saving lives in military aviation today. What impressed you most about this forgotten hero of World War II? Let me know in the comments below. And if you want to see more untold stories from WWII's greatest innovations, subscribe and hit that notification bell so you don't miss the next deep dive. Thanks for watching WWII Aviation, and I'll see you in the next one.